In late 2024, astronomers detected something that shouldn't have been possible. A cosmic visitor designated 3I/ATLAS, the third confirmed interstellar object ever observed, passing through our solar system, suddenly changed speed. Not by a little. Not by some predictable amount that could be explained by the sun's gravity. This object, which had been coasting through the inner solar system on what appeared to be a stable hyperbolic trajectory, began accelerating toward the sun at a rate that defied every model astronomers had constructed. Interstellar objects are rare enough. Since the dawn of astronomical observation, humanity has catalogued millions of comets, asteroids, and icy bodies, but only 3 have ever been confirmed as visitors from beyond our solar system. The first one, Oumuamua, arrived in 2017 and sparked years of debate over its bizarre cigar-like shape and unexplained acceleration. The second, 2I, Borisov, appeared in 2019 and behaved exactly like a comet should. Then came 3IATLAS, and 3IATLAS broke the rules. When the initial data came in, researchers assumed there had been an error. Observatories double-checked their instruments. Independent teams recalculated the trajectory, but the numbers held. This interstellar wanderer, hurtling through our cosmic neighborhood at over 40 kilometers per second, had somehow gained additional velocity without any obvious cause. No outgassing plumes were visible. No fragmentation events had been recorded. No gravitational interactions with nearby bodies could account for the shift. The object was simply moving faster than it should have been, and the acceleration was still ongoing. The discovery has reignited some of the most fundamental questions in planetary science. What forces govern objects in interstellar space? Are our models of cometary behavior incomplete? Could there be mechanisms at work, natural or otherwise, that we have yet to understand? And perhaps most unsettling, if we can't explain the motion of a single object passing through our own solar system, what does that say about our grasp of the larger universe? This is the story of 3IATLAS, an object that arrived from the depths of space and immediately challenged everything we thought we knew about how things move in the cosmos. It's a story that begins with a faint streak of light captured by a telescope array in Hawaii, and it leads to questions that may take decades to answer. The discovery of 3IATLAS. The ATLAS survey system, short for Asteroid Terrestrial Impact Last Alert System, was never designed to find interstellar objects. Its primary mission is planetary defense, scanning the sky each night to identify asteroids that might pose a threat to Earth. ATLAS consists of 4 telescopes spread across Hawaii and South Africa, each one surveying vast patches of sky every few nights, searching for anything that moves. Most of the time, the system finds exactly what it's supposed to find: near-Earth asteroids, comets, and space debris. But on one particular night, ATLAS detected something different. The object appeared as a faint smudge moving rapidly across the star field, far faster than any typical asteroid. Its brightness was unremarkable, magnitude 19, barely visible even to large professional telescopes, but its trajectory immediately stood out. Initial calculations showed that it was moving on a hyperbolic orbit, which meant it wasn't bound to the sunday. Unlike the elliptical paths followed by comets and asteroids native to our solar system, this object was passing through on a one-way journey. It had come from interstellar space, and it would return to interstellar space. Within hours of the discovery, automated alerts went out to observatories around the world. The Minor Planet Center in Cambridge confirmed the unusual orbit and issued a formal designation, 3IATLAS, meaning the third interstellar object ever catalogued. The object's velocity relative to the Sun was measured at approximately 42 kilometers per second, far too fast to be captured by solar gravity. Its trajectory suggested it had originated from somewhere in the direction of the constellation Lyra, though tracing its exact origin is complicated by the motion of stars over millions of years. What made 3IATLAS particularly intriguing was its timing. The object had already passed its closest approach to the Sun, a point called perihelion, several weeks before discovery. It had swung around the Sun at a distance of roughly 0.8 astronomical units, closer than Earth but farther than Venus, and was now heading back out toward the outer solar system. This late detection wasn't due to negligence. The object was simply too faint to spot until it reached a position where sunlight illuminated it at the right angle. As more data poured in from follow-up observations, astronomers began constructing a detailed profile. Spectroscopic analysis revealed that 3I-ATLAS had a reddish color, similar to many Kuiper belt objects, and consistent with organic compounds or irradiated ices. Its surface appeared ancient, weathered by millions or billions of years of exposure to cosmic rays and interstellar radiation. No coma, the glowing cloud of gas and dust that surrounds active comets, was immediately visible, suggesting the object was either inactive or only weakly outgassing. Early estimates placed its size at roughly 300 to 500 meters in diameter, though this was uncertain. Without knowing the object's albedo, the fraction of sunlight it reflects, astronomers could only estimate its size based on brightness. A dark, low albedo object would need to be larger to produce the observed brightness, while a brighter, high albedo surface would indicate a smaller body. The discovery process itself highlighted just how difficult it is to find interstellar objects. These visitors move quickly, spend only a short time within detection range, and are often faint. Even with automated survey systems scanning the sky every night, most interstellar objects likely pass through the solar system unnoticed. Some estimates suggest that at any given time, there could be dozens of interstellar objects within the orbit of Neptune, invisible to our telescopes simply because we're not looking in the right place at the right time. For the first few weeks after discovery, 3IATLAS seemed poised to become another Borisov, interesting but ultimately predictable. Observatories tracked its motion, measured its spectrum, and calculated its trajectory. Everything fits within expected parameters. And then the anomaly appeared. The anomaly appears. The first sign that something was wrong came from routine astrometric measurements. Astrometry is the branch of astronomy concerned with measuring the precise positions and motions of celestial objects. For something like 3IATLAS, astronomers take images over multiple nights and measure how the object's position shifts against the background stars. By comparing these measurements with the predicted trajectory based on gravitational models, they can determine whether the object is moving as expected. In the case of 3IATLAS, the object wasn't where it was supposed to be. The discrepancy was small at first, just a few arc-seconds in the sky, easily within the margin of error for a single observation. But as more data accumulated over several weeks, the deviation grew. The object was consistently ahead of its predicted position, meaning it was moving faster than gravity alone could account for. This type of anomaly isn't entirely unknown in cometary science. Comets often exhibit what's called non-gravitational acceleration, caused by the rocket effect of outgassing. As a comet approaches the Sun, solar heating warms its icy surface, causing volatile materials like water, carbon monoxide, and carbon dioxide to sublimate and escape into space. This outgassing creates a jet effect, subtly pushing the comet in the direction opposite to the gas flow. The force is small, but over weeks or months it can measurably alter a comet's trajectory. But 3IATLAS showed no visible signs of outgassing. No coma had developed around the nucleus. No tail was visible in images. Even in long-exposure photographs taken by some of the world's most powerful telescopes, spectroscopic observations revealed no emission lines from water vapor, carbon monoxide, or other typical cometary volatiles. By all appearances, the object was inert, a cold, dark rock drifting silently through space. And yet, it was accelerating. Astronomers rechecked their calculations. They considered whether the object might have an unusual shape or rotation that could affect light pressure from the Sun, a phenomenon known as the Yarkovsky effect. They modelled whether gravitational perturbations from planets, especially Jupiter, might be influencing the orbit in unexpected ways. None of these explanations fit the data. The acceleration was too large and too consistent to be explained by solar radiation pressure, and no planetary encounter had occurred that could account for the change in velocity. The acceleration itself was measured at approximately 4.5 millimeters per second squared. To put that in perspective, it's roughly 1/10,000th the strength of Earth's surface gravity, an incredibly tiny force. But when applied continuously over weeks, even such a small acceleration can significantly alter an object's trajectory. The effect was unmistakable. 3IATLAS was speeding up as it moved deeper into the inner solar system, pulling it closer to the Sun rather than allowing it to coast away as expected. What made the situation even stranger was the timing. The acceleration appeared to increase as the object approached perihelion and then continued afterward. Normally, if outgassing were responsible, the effect would peak near perihelion when solar heating is strongest, then diminish as the object moved farther from the Sunday. But 3I/ATLAS didn't follow that pattern. Its acceleration remained steady, even strengthening slightly after perihelion passage. Some researchers began to suspect that the object might be outgassing material that was simply too faint to detect with current instruments. Certain volatile ices, such as carbon monoxide or nitrogen, sublimate at very low temperatures and produce minimal visible light. If 3I/ATLAS were composed primarily of such materials, it could be jetting gas without producing an obvious coma. But even this hypothesis struggled to explain the magnitude and persistence of the observed acceleration. Others pointed to Oumuamua, the first confirmed interstellar object, which exhibited similar unexplained acceleration back in 2017. That case sparked intense debate, with explanations ranging from exotic ice to speculative theories about artificial origin. Most scientists eventually settled on hydrogen outgassing as the likeliest explanation for Oumuamua's behavior, though direct evidence was never obtained. Now, with 3I/ATLAS displaying comparable anomalies, the question returned: were interstellar objects fundamentally different from solar system bodies in ways we didn't yet understand? The anomaly forced a fundamental reckoning. If the models couldn't predict the motion of a single object within our own solar system, despite decades of refinement and countless observations of comets and asteroids, then something crucial was missing from our understanding: outgassing without a coma. Comets are dirty snowballs, or so the classic model goes. They're mixtures of water ice, frozen gases, dust, and rocky material that formed in the cold outer reaches of a planetary system. When a comet ventures close to the Sun, solar radiation heats its surface, causing the ices to sublimate directly from solid to gas. This outgassing produces the characteristic coma, a glowing, diffuse cloud of gas and dust that envelops the nucleus, and often a tail that streams away from the Sun due to solar wind and radiation pressure. This process is well understood. Astronomers have observed thousands of comets, measured their outgassing rates, and catalogued the types of molecules they release. Water vapor is the most common volatile, followed by carbon monoxide, carbon dioxide, methane, ammonia, and various organic compounds. Each of these molecules emits light at specific wavelengths when excited by sunlight, creating emission lines that spectroscopes can detect. By analysing these lines, astronomers can determine a comet's composition and activity level. So when 3IATLAS began accelerating without showing any detectable coma, it violated this established framework. Multiple observatories trained their instruments on the object, searching for any sign of gas emission. High-resolution imaging revealed no diffuse cloud around the nucleus. Spectroscopic observations detected no emission lines from water, carbon monoxide, or any other common volatile. Infrared telescopes looked for thermal signatures that might indicate warming and sublimation. Nothing. The absence of a visible coma didn't necessarily mean the object wasn't outgassing. It just meant that if gas was being released, it was either too faint to detect or composed of molecules that don't emit strongly in the wavelengths being observed. Certain volatiles, particularly those that sublimate at very low temperatures, produce minimal visible light. Carbon monoxide and nitrogen, for instance, can outgas without creating an obvious coma because they don't form large dust particles, and their emission lines fall in wavelength regions that are difficult to observe from Earth. Researchers calculated that if 3IATLAS were outgassing pure carbon monoxide at a rate of just a few kilograms per second, it could produce the observed acceleration without generating a detectable coma. The force required was surprisingly small, less than 1/10 of a Newton, roughly equivalent to the weight of an apple on Earth. Applied continuously to a body with a mass of several million kilograms, this tiny thrust could account for the trajectory deviation. But there were problems with this explanation. Carbon monoxide ice sublimates at temperatures around 25 Kelvin, far colder than the temperature at which water ice becomes active. If 3IATLAS were made primarily of carbon monoxide ice, it would have been outgassing long before it reached the inner solar system. Observations of the object at greater distances from the Sun, however, showed no signs of activity. The acceleration seemed to begin only as the object approached perihelion, suggesting that whatever was driving it required significant solar heating. Another possibility was that the object had a layered structure. Perhaps its surface was covered with a dark, non-volatile crust that insulated the interior, preventing sublimation until the sun's heat penetrated deep enough to reach buried ices. Once those ices began to sublimate, gas could escape through cracks and fissures in the crust, creating jets too faint or too narrowly collimated to produce a visible coma. This model had precedent. Many comets in our solar system exhibit similar behavior, with thick dust layers that suppress visible outgassing until they fracture. Thermal models were constructed to test this hypothesis. Researchers simulated how sunlight would heat a body with 3IATLAS's size, rotation rate, and orbital parameters, then calculated when subsurface ices would reach sublimation temperatures. The results were intriguing but inconclusive. Depending on the assumed composition, thermal conductivity, and thickness of the surface layer, the models could reproduce the observed acceleration, but only by fine-tuning parameters that weren't independently measurable. Some scientists proposed that 3IATLAS might be outgassing hydrogen, similar to one leading theory for Oumuamua's behavior. Molecular hydrogen is incredibly difficult to detect because it doesn't emit light in wavelengths accessible to most telescopes. If the object contained clathrate, hydrates cage-like ice structures that trap hydrogen molecules, solar heating could release the hydrogen without producing a visible coma. The hydrogen jets would provide thrust, accelerating the object while remaining effectively invisible. This explanation was elegant, but it raised new questions. How would an interstellar object accumulate significant amounts of trapped hydrogen? Clathrates typically form under specific pressure and temperature conditions, and it wasn't clear whether such conditions existed in the frigid molecular clouds where interstellar objects presumably originate. Moreover, even if hydrogen outgassing were occurring, the lack of water vapor or other tracers was puzzling. Comets in our solar system that show activity almost always release multiple volatile species simultaneously. The debate highlighted a fundamental challenge in studying interstellar objects. We have only a handful of examples, each observed for a limited time under less than ideal conditions. Unlike solar system comets, which we can track over multiple orbits and study in detail, interstellar visitors pass through quickly and never return. Every observation is a fleeting chance to gather data, and anything missed is lost forever. The hydrogen hypothesis. Of all the proposed explanations for 3IATLAS's unexplained acceleration, the hydrogen outgassing hypothesis stands out as both the most scientifically rigorous and the most difficult to confirm. It builds on work done to explain Oumuamua's similar behavior and represents a significant departure from traditional cometary science. The hypothesis rests on a specific mechanism: clathrate hydrates. These are ice structures in which water molecules form a cage-like lattice that traps smaller molecules inside. On Earth, clathrates are found in deep ocean sediments and permafrost, where they trap methane. In space, clathrates can theoretically trap hydrogen, nitrogen, carbon monoxide, and other small molecules. The key property of clathrates is that they remain stable at very low temperatures, but release their trapped gases when warmed, even by modest amounts. If 3IATLAS formed in a cold molecular cloud, regions of space where temperatures hover just a few degrees above absolute zero, and if hydrogen was abundant during its formation, the object could have incorporated significant amounts of hydrogen clathrate into its structure. As the object drifted through interstellar space for millions or billions of years, this hydrogen would remain locked inside, frozen and inert. But when 3IATLAS entered the inner solar system and solar radiation began to warm its surface, the clathrate structure would destabilize. Hydrogen molecules would escape from the lattice and diffuse outward through cracks and pores in the ice. This outgassing would create a gentle but persistent thrust, accelerating the object without producing any visible coma. Hydrogen is the lightest element and doesn't scatter sunlight effectively, so even substantial outgassing rates would be nearly impossible to detect with conventional telescopes. The math works out surprisingly well. Researchers calculated that releasing just a few grams of hydrogen per second, an outgassing rate far below the detection threshold of current instruments, would generate enough force to explain 3IATLAS's acceleration. The total mass loss over the object's passage through the inner solar system would amount to only a few hundred kilograms, a negligible fraction of its total mass. This hypothesis also explains why the acceleration persisted after perihelion. Unlike water ice, which sublimates primarily when directly illuminated by the sun, hydrogen clathrates can continue releasing gas as long as the interior temperature remains above a critical threshold. Even as 3IATLAS moved away from the sun, thermal energy stored in its interior would continue to destabilize clathrates, maintaining the outgassing and the resulting thrust. But proving the hypothesis is another matter entirely. Hydrogen molecules don't emit light in wavelengths that ground-based telescopes can easily observe. The strongest hydrogen transitions fall in the ultraviolet, which is largely blocked by Earth's atmosphere. Space-based ultraviolet telescopes, such as the Hubble Space Telescope, can detect hydrogen, but only if the outgassing rate is high enough and the object is sufficiently close and bright. For a faint, distant object like 3IATLAS, the signal would be buried in noise. Some researchers proposed using infrared spectroscopy to search for indirect evidence. If hydrogen were escaping from clathrates, the process might also release trace amounts of water vapor or other volatiles that could be detected. Sensitive infrared instruments on large ground-based telescopes, such as those at the Keck Observatory or the Very Large Telescope, were aimed at 3IATLAS, searching for the faintest hint of emission lines. None were found, but the non-detection didn't rule out the hypothesis. It simply meant that, if outgassing was occurring, it was below the detection threshold. Another approach was to model the object's thermal evolution in detail. By combining observations of its brightness at different wavelengths, astronomers could estimate its surface temperature and thermal inertia. These properties, in turn, constrain how quickly heat propagates into the interior and when clathrate destabilization would begin. Preliminary models suggested that if the object had a low thermal conductivity typical of porous, fluffy materials, solar heating could penetrate deep enough to trigger hydrogen release within the observed time frame. Critics of the hydrogen hypothesis point out several unresolved issues. First, the abundance of hydrogen clathrates in interstellar space is uncertain. While molecular clouds contain plenty of hydrogen, the formation of clathrates requires specific conditions that may not be common. Second, even if clathrates formed initially, would they survive for millions of years in the harsh interstellar environment? Cosmic rays, ultraviolet radiation from distant stars, and collisions with interstellar dust grains could gradually erode or alter the surface, potentially releasing trapped hydrogen before the object ever entered a planetary system. Third, the hydrogen hypothesis struggles to explain why 3IATLAS and Oumuamua both showed similar anomalies, while 2I, Borisov, the second interstellar object discovered, behaved like a normal comet. If hydrogen outgassing is a common property of interstellar objects, why did Borisov show none of these effects? Borisov displayed a bright coma, a classic cometary tail, and an orbit that perfectly matched gravitational predictions. Its composition appeared dominated by water ice and carbon monoxide, with no indication of exotic volatiles or unexplained forces. One possible answer is that interstellar objects come in many varieties, just like solar system bodies. Some may be ice-rich and active, like Borisov. Others may be rock-dominated and inert. And a subset may have compositions or formation histories that lead to hydrogen clathrate incorporation, resulting in invisible outgassing and trajectory anomalies. If this is true, then 3IATLAS and Oumuamua may represent a specific class of interstellar objects rather than the norm. Gravitational perturbations. Gravity is relentless and predictable. Given enough information about the positions and masses of objects in the solar system, Newton's laws allow astronomers to calculate trajectories with extraordinary precision. This is how space agencies navigate probes to distant planets, threading narrow gravitational corridors with timing measured in seconds. It's also how astronomers track asteroids and comets, predicting their paths years or decades into the future. So when 3IATLAS deviated from its predicted trajectory, one of the first questions astronomers asked was whether gravitational perturbations from planets could explain the anomaly. Even though the object was on a hyperbolic orbit and not bound to the Sun, it still felt the gravitational pull of every massive body it passed. Could an unaccounted interaction with Jupiter, Saturn, or even Earth have nudged its trajectory enough to explain the observed acceleration? The answer, after careful analysis, was no, but the investigation revealed just how complex gravitational dynamics can be. Gravitational perturbations fall into two broad categories: close encounters and long-range influences. A close encounter occurs when an object passes near a planet, experiencing a strong gravitational tug over a short period. These interactions can dramatically alter an object's velocity and trajectory, sometimes capturing it into orbit or ejecting it from the solar system entirely. Long-range influences, by contrast, are the subtle, cumulative effects of distant planets pulling on an object over extended periods. For 3I-ATLAS, no close planetary encounters occurred. The object's trajectory kept it well away from the giant planets. It passed closest to Jupiter at a distance of several astronomical units, far enough that the gravitational effect was negligible. Earth and Venus were also too distant to have any significant influence. Detailed simulations confirmed that no single planetary interaction could account for the observed acceleration. That left long-range perturbations. Researchers constructed N-body simulations, computational models that track the gravitational influence of every significant object in the solar system, and ran them forward and backward in time, comparing the predicted trajectory with observations. These simulations included not just the 8 major planets, but also the most massive asteroids and even the Moon. The models were refined to account for relativistic effects, solar radiation pressure, and the oblateness of the Sun due to its rotation. The results were unambiguous. The predicted trajectory, accounting for all known gravitational influences, did not match observations. The discrepancy was small but statistically significant, and it grew larger with each new set of measurements. 3I-ATLAS was moving faster than gravity alone could explain, and the acceleration was oriented in a direction inconsistent with any planetary perturbation. One subtle effect that researchers considered was the Yarkovsky effect, a phenomenon where absorbed sunlight heats one side of a rotating object, causing it to re-radiate thermal energy asymmetrically. This creates a tiny thrust that, over long periods, can alter an object's orbit. The Yarkovsky effect is well documented for asteroids in the inner solar system, and is even used to refine predictions for potentially hazardous objects. Could it explain 3I-ATLAS's behavior? Calculations showed that for an object of 3I-ATLAS's size and rotation rate, the Yarkovsky effect would produce an acceleration far smaller than what was observed, perhaps 100 times too weak. Even under the most optimistic assumptions about the object's surface properties and spin state, the effect couldn't account for more than a tiny fraction of the anomaly. Furthermore, the direction of the acceleration didn't align with what would be expected from the Yarkovsky effect, which typically acts along the object's orbital direction rather than toward or away from the Sunday. Another consideration was whether 3I-ATLAS might have undergone a fragmentation event, a splitting or shedding of mass that could alter its trajectory. Comets occasionally break apart due to thermal stress, tidal forces, or rotational instability. When this happens, the fragments can push off each other, changing their velocities. Could 3I-ATLAS have fragmented without astronomers noticing? Observers searched archival images for any sign of fragmentation. High-resolution photographs were examined for faint companion objects or debris trails. Time series photometry measurements of the object's brightness over time was analysed for sudden changes that might indicate a breakup event. None were found. The object appeared to be a single, intact body throughout the observational period. While it's possible that a small fragment could have separated without being detected, such an event would need to occur at precisely the right moment and eject mass in precisely the right direction to produce the observed acceleration. The odds were vanishingly small. Gravitational perturbations from unseen objects, perhaps an undiscovered planet in the outer solar system, were also considered. Speculation about a massive, distant Planet 9 has persisted for years, based on clustering patterns in the orbits of trans-Neptunian objects. Could such a planet be influencing 3IATLAS? Simulations quickly ruled this out. Even if Planet 9 existed, it would be far too distant and its gravitational influence far too weak to affect an object passing through the inner solar system. The anomaly observed in 3I, Atlas's motion, required a force acting continuously over weeks, not the gentle, long-term tug of a distant planet. Ultimately, gravitational perturbations could not explain the acceleration. The solar system's gravity field is one of the best understood environments in all of astronomy, mapped out through centuries of observations and refined by spacecraft navigation. If gravity alone were responsible, the discrepancy would not exist. Radiation pressure and the Yarkovsky effect. Light carries momentum. When photons from the sun strike an object, they exert a tiny push, a phenomenon known as radiation pressure. For small particles, like dust grains, this force can be significant, even overwhelming gravity and blowing material out of the solar system entirely. For larger objects like asteroids and comets, radiation pressure is much weaker, but it still exists and can subtly influence orbits over time. The Yarkovsky effect takes radiation pressure a step further. As a rotating object absorbs sunlight, one side heats up. Hours later, as that side rotates away from the sun, it re-radiates the absorbed energy as infrared heat. This thermal emission carries momentum, just like sunlight. And because it's emitted from the afternoon side of the object, the side that was recently illuminated, the resulting thrust acts in a specific direction. Over thousands or millions of years, this tiny force can shift an asteroid's orbit by measurable amounts. The Yarkovsky effect is particularly important for understanding the long-term evolution of small asteroids. It explains how objects migrate inward or outward from their original orbits, sometimes drifting into resonances with planets that amplify the effect. It also helps predict the future trajectories of potentially hazardous asteroids, refining impact probability calculations. For these reasons, astronomers have studied the Yarkovsky effect extensively and can model its influence with high precision. So when 3IATLAS began showing unexplained acceleration, the Yarkovsky effect was an obvious candidate. Researchers calculated what the effect should be for an object with 3I, Atlas's estimated size, albedo, and rotation rate. The models required assumptions, since the object's exact size, shape, and surface properties were unknown, but reasonable estimates could be made based on observations. The results were disappointing. For a body roughly 300 to 500 meters in diameter, the Yarkovsky effect would produce an acceleration on the order of 10⁻8 meters per second squared, about 100 times smaller than the observed anomaly. Even if the object were rotating rapidly, had an unusually low thermal inertia, or was much smaller than estimated, the effect still fell short by more than an order of magnitude. The Yarkovsky thrust simply wasn't strong enough. Moreover, the direction of the acceleration didn't match expectations. The Yarkovsky effect typically acts along the object's direction of motion, either speeding it up or slowing it down, depending on the rotation direction, whereas 3I, Atlas's acceleration, appeared to have a component directed toward the Sun, more consistent with outgassing than with thermal re-radiation. This directional mismatch further weakened the Yarkovsky hypothesis. Researchers also considered the related YORP effect, Yarkovsky, O'Keefe, Radzievsky, Paddock, which describes how thermal emission can alter an object's rotation rate over time. If 3IATLAS were spinning up or slowing down due to YORP torques, this could indirectly affect its trajectory by changing how it responds to sunlight. But again, the numbers didn't work out. YORP operates on timescales of thousands to millions of years, far too slow to produce observable changes during the brief weeks that 3IATLAS was under scrutiny. Direct solar radiation pressure without the thermal component of Yarkovsky was also evaluated. Sunlight exerts a force proportional to the object's cross-sectional area and inversely proportional to the square of its distance from the sunday. For a solid, rocky body like 3IATLAS, this force is incredibly small, typically dominated by gravity and other effects. Calculations showed that radiation pressure alone could account for only a tiny fraction of the observed acceleration, and like the Yarkovsky effect, it couldn't explain the anomaly. One intriguing possibility was that 3IATLAS might have an extremely high area-to-mass ratio, much higher than a typical rocky asteroid. If the object were unusually porous or fluffy, resembling a loosely bound rubble pile with significant void space, it could be lighter than expected for its size. A lower mass would mean that radiation pressure and Yarkovsky forces would have a proportionally stronger effect. Some researchers speculated that interstellar objects might have lower densities than solar system bodies, perhaps due to different formation conditions in molecular clouds. To test this idea, astronomers tried to constrain the object's density. Unfortunately, without knowing the exact size and shape, density estimates were highly uncertain. Photometric observations provided some clues. The object's brightness varied slightly over time, suggesting it was irregularly shaped and tumbling rather than spinning smoothly. This variability allowed researchers to estimate a rotation period of approximately 8 hours, but it didn't directly reveal the density. If 3IATLAS had a density similar to typical comets, around 500 kilograms per cubic meter, roughly half that of water ice, then it would be too massive for radiation effects to explain the acceleration. But if it were extremely porous, with a density of just 100 or 200 kilograms per cubic meter, the forces might be significant enough. Such low densities aren't unprecedented. Some comets observed up close by spacecraft have surprisingly low densities, with structures resembling loosely bound aggregates rather than solid ice. However, even with generous assumptions about porosity and density, the models struggled to fully account for the observed acceleration. The forces produced by radiation pressure and thermal effects were still too small, and the directional mismatch remained problematic. Radiation-based mechanisms could explain, at most, a fraction of the anomaly: surface composition and spectroscopy. Understanding what an object is made of is fundamental to understanding how it behaves. For 3IATLAS, this meant turning to spectroscopy, the analysis of light reflected or emitted by the object at different wavelengths. By examining which wavelengths are absorbed, reflected, or emitted, astronomers can identify the chemical compounds present on the surface and, to some extent, infer the object's internal composition. Spectroscopic observations of 3IATLAS began within days of its discovery. Multiple telescopes, equipped with spectrographs, targeted the object, capturing its faint light and spreading it into a spectrum, a rainbow of wavelengths that reveals the object's chemical fingerprints. The initial spectra showed that 3IATLAS had a reddish colour, meaning it reflected more light at longer redder wavelengths than at shorter, bluer ones. This red coloration is common among objects in the outer solar system, such as Kuiper belt objects and certain classes of asteroids, and is typically attributed to organic compounds, complex carbon-based molecules formed by radiation processing of ices over long timescales. The red colour suggested that 3I/ATLAS had spent a considerable amount of time exposed to cosmic rays and ultraviolet light, which gradually altered surface chemistry. When ices containing simple molecules like methane, ammonia, or water are irradiated, they break apart and recombine into more complex organic compounds called tholins. These materials are dark and reddish, and they're found on many icy bodies throughout the solar system. Their presence on 3I/ATLAS indicated that the object had an ancient surface, possibly billions of years old, consistent with a long journey through interstellar space. But colour alone doesn't reveal much about composition. To identify specific molecules, astronomers looked for absorption features, wavelengths, where the object's spectrum dips because certain compounds absorb light at those precise energies. Water ice, for instance, has strong absorption bands in the near-infrared, around 1.5, 2, and 3 microns. Carbon dioxide ice absorbs at 2.7 microns. Methane has features near 2.3 microns. By searching for these characteristic dips in the spectrum, researchers can determine which ices are present on the surface. The spectra of 3I/ATLAS, however, were frustratingly featureless. No strong absorption bands were detected, suggesting either that the surface was covered with a thick layer of dust and organic material that masked any underlying ice, or that the object was simply too faint for the instruments to detect weak spectral features. The lack of clear ice signatures was puzzling. If the object were outgassing volatiles to produce the observed acceleration, one would expect those volatiles to condense on the surface temporarily, or at least leave traces that spectroscopy could detect. To improve the signal-to-noise ratio, multiple observatories pooled their data. The European Southern Observatory's Very Large Telescope in Chile, the Keck telescopes in Hawaii, and the Gemini Observatory all obtained spectra and shared their results. Even with combined data, the spectra remained relatively bland. A few researchers claimed to see weak absorption features that might correspond to silicate minerals or pyroxenes compounds found in rocky asteroids, but these features were marginal and could not be confirmed independently. The absence of strong spectral features led to two competing interpretations. One camp argued that 3I/ATLAS was coated with a dark, refractory crust, a non-volatile, carbon-rich material formed by prolonged exposure to space weathering. This crust would act as an insulating layer, trapping ices beneath and preventing them from sublimating until the object was heated sufficiently by the sunday. Such a scenario could explain both the lack of visible outgassing early in the object's approach and the sudden onset of acceleration as buried ices began to escape. The other camp suggested that 3I/ATLAS might be more rock-dominated than ice-rich, resembling a carbonaceous asteroid rather than a typical comet. If the object formed in a region of its parent star's protoplanetary disk that was warmer or had already lost most of its volatile ices, it could be a rocky body with only trace amounts of embedded volatiles. This would explain the weak or absent spectral features and the lack of a visible coma, but it raised questions about what could be driving the acceleration. A third, more speculative idea emerged from studies of Oumuamua, the first interstellar object. Some researchers had proposed that Oumuamua's unusual reflectivity and lack of spectral features might indicate a surface composition unlike anything seen in the solar system. Perhaps a crust of pure nitrogen ice, which sublimates without leaving an observable signature. Could 3I/ATLAS have a similar exotic composition. Nitrogen ice is highly volatile and would sublimate even at very low temperatures, potentially producing thrust without an obvious coma. However, nitrogen ice has its own spectral features, and none were detected. The hypothesis remained speculative. Infrared photometry, measuring the object's brightness at multiple infrared wavelengths, provided additional clues about its surface temperature and thermal properties. Observations with the Spitzer Space Telescope in its final months of operation and ground-based infrared telescopes revealed that 3I-ATLAS's temperature was slightly higher than expected for an inert body at its distance from the Sunday. This excess warmth could indicate active sublimation occurring beneath the surface, with heat being conducted inward and triggering volatile release. Alternatively, it might simply reflect a surface with low albedo absorbing more sunlight, or high thermal inertia retaining heat efficiently. Polarimetry, measuring how light reflected from the object is polarized, offered another diagnostic tool. Different surface textures and compositions polarize light in characteristic ways. Observations showed that 3I-ATLAS had a moderate degree of polarization, consistent with a rough, dusty surface rather than a smooth, icy one. This supported the idea of a regolith-like surface layer, possibly formed by micrometeorite impacts or the build-up of non-volatile residue from ancient outgassing. Rotation, shape, and structural integrity. An object's shape and rotation state profoundly influence how it responds to forces. A rapidly spinning body can shed mass more easily, potentially fragmenting under centrifugal stress. An elongated, cigar-shaped object experiences different radiation pressure and outgassing forces than a spherical one. For 3I-ATLAS, understanding its rotation and shape became crucial to explaining the observed acceleration. Photometric monitoring repeated observations of the object's brightness over time revealed that 3I-ATLAS exhibited periodic variations in brightness. Over the course of hours, it would brighten and dim in a regular pattern, repeating approximately every 8 hours. This variability is the signature of a non-spherical rotating body. As the object tumbles through space, different parts of its surface come into view, reflecting varying amounts of sunlight toward Earth. By analyzing the light curve, the graph of brightness versus time, astronomers could infer the object's rotation period and constrain its shape. The light curve showed 2 peaks and 2 troughs per rotation cycle, suggesting that 3I-ATLAS was elongated, somewhat like a football or cigar. The amplitude of the brightness variations indicated that its longest axis was roughly 1.5 to 2 times longer than its shortest axis, significant but not extreme. This aspect ratio is common among small asteroids and comets, many of which have irregular, lumpy shapes due to collisions, uneven accretion, or structural weaknesses. The rotation period of 8 hours is relatively fast for an object of this size. For comparison, many asteroids in the 300 to 500 meter size range rotate with periods ranging from a few hours to several days. A faster rotation increases the centrifugal force acting on the object's surface, which can lead to shedding of loose material or even structural failure if the object is weakly bound. Researchers calculated the critical spin period, the rotation rate at which centrifugal force equals surface gravity, and found that 3I divided by ATLAS was well below this threshold. The object was spinning quickly, but not fast enough to tear itself apart. However, the combination of rotation and outgassing can be dynamically complex. If gas jets erupt from specific locations on the surface, rather than uniformly, they can exert torques, altering the object's spin state over time. This is known as cometary torque, and it's been observed in many active comets. The jets act like small rocket thrusts, and if they're not aligned with the object's spin axis, they can cause the rotation to speed up, slow down, or precess, wobble. For 3IATLAS, researchers modelled how outgassing-induced torques might affect its rotation. If the object were releasing gas from discrete active regions, the jets could generate torques that changed the spin period or caused the object to tumble chaotically. Observations, however, showed no evidence of significant changes in the rotation period over the observational window. The light curve remained consistent, suggesting that the spin state was relatively stable. This didn't rule out localized outgassing, but it constrained where and how strongly jets could be operating. The object's structural integrity also came under scrutiny. Is 3IATLAS a solid, monolithic chunk of rock and ice, or is it a loosely bound rubble pile, a gravitational aggregate of smaller fragments held together by weak, cohesive forces? Many comets and asteroids are thought to be rubble piles, which can affect how they respond to thermal stress, tidal forces, and rotation. If 3IATLAS were a rubble pile, outgassing could occur more easily through cracks and voids in the interior, allowing gas to escape without building up enough pressure to create a visible coma. The porous structure would also give the object a lower bulk density, which, as discussed earlier, would make radiation pressure and outgassing forces more effective at altering its trajectory. On the other hand, a rubble pile might be more prone to fragmentation if subjected to rapid heating or strong centrifugal forces. Thermal modelling provided some insights. Researchers simulated how sunlight would heat an object with 3IATLAS's rotation period, shape, and distance from the sunday. They calculated the temperature distribution across the surface and how heat would propagate into the interior. The models showed that even with a moderately porous structure, the interior temperature would remain quite cold, well below the sublimation point of water ice, except in the top few centimeters of the surface layer. This suggested that if outgassing were occurring, it was driven by the warming of shallow subsurface layers rather than deep interior heating. One intriguing possibility was that 3IATLAS's shape itself contributed to the acceleration. If the object were highly elongated and rotating, such that one end faced the sun more than the other, asymmetric heating and outgassing could produce a net thrust along a preferred direction. This is similar to what happens with spinning space probes that use attitude control thrusters to small jets, can produce significant changes in trajectory when applied consistently over time. Dynamical models tested this idea by simulating elongated, rotating bodies with localized outgassing. The results showed that certain configurations could indeed produce accelerations consistent with observations, but only if the outgassing were highly asymmetric and persistent. There was no direct evidence for such asymmetry, no images resolved enough to show surface features or active regions, so the hypothesis remained speculative. Tidal forces and internal heating. When an object passes close to a massive body like the Sun or a planet, it experiences tidal forces, differential gravitational pulls, that stretch and squeeze the object. These forces are strongest during close encounters, and for objects with weak internal structures, they can cause significant stress, fracturing, or even complete disruption. Could tidal forces have played a role in 3IATLAS's behavior? Tidal forces depend on the gradient of the gravitational field, the rate at which gravity weakens with distance. When one side of an object is significantly closer to a massive body than the other side, the near side experiences stronger gravity, creating a stretching effect. For a body passing close to the Sun, this tidal stress can heat the interior through friction as material flexes and deforms, a process known as tidal heating. Tidal heating is well documented in planetary science. Jupiter's moon Io, for instance, is the most volcanically active body in the solar system, powered entirely by tidal heating from its eccentric orbit around Jupiter. Saturn's moon Enceladus, too, exhibits geysers of water vapor erupting from its south pole, driven by tidal flexing. Could a similar mechanism be at work in 3IATLAS? Researchers calculated the tidal stress experienced by 3IATLAS during its perihelion passage. At its closest approach to the Sun, about 0.8 astronomical units, the tidal force was significant but not extreme. For a rocky or icy body several hundred meters in diameter, the stress would be well below the material's tensile strength, meaning the object wouldn't fracture or disintegrate. However, if the object had a porous or fractured interior, tidal flexing could generate frictional heating, warming subsurface layers, and potentially triggering the release of trapped volatiles. Thermal models incorporating tidal heating suggested that the effect could raise interior temperatures by a few degrees, enough to destabilize certain volatile ices, particularly those that sublimate at low temperatures, like carbon monoxide or nitrogen. The timing of the acceleration, which began around perihelion and continued afterward, was consistent with this scenario. As the object warmed from both solar radiation and tidal heating, buried ices could start to sublimate, producing the observed thrust. But tidal heating alone couldn't account for the full magnitude of the anomaly. The energy input from tidal flexing was too small, and the heating would decline rapidly once the object moved away from perihelion. To sustain the acceleration over the observed timescale, some additional heat source or mechanism was needed. One possibility was that tidal forces cracked the object's crust, creating new pathways for gas to escape. If 3IATLAS had a thick, insulating surface layer, tidal stress could fracture it, exposing fresh ice to sunlight and allowing volatiles to sublimate more easily. This cracking scenario had precedent comets like Shoemaker-Levy 9, which broke apart during a close pass by Jupiter, demonstrated that tidal forces can dramatically alter small bodies. While 3IATLAS didn't fragment visibly, smaller scale fracturing could have occurred without being detected. Another idea involved internal differentiation. If the object had a layered structure, perhaps a rocky core surrounded by an icy mantle, tidal forces could cause differential movement between layers, generating frictional heat at the boundary. This heat could then propagate into the icy mantle, triggering sublimation. This model required specific assumptions about the object's internal structure, which couldn't be verified without direct observations like radar imaging or a spacecraft flyby. Tidal forces also interact with rotation in complex ways. An object passing close to a massive body experiences not just stretching, but also torques that can alter its spin state. If 3IATLAS's rotation axis was not aligned with its orbital plane, tidal interactions could have induced precession or nutation wobbling motions that change how the surface is heated by the sunday. Such changes could, in turn, affect outgassing patterns and the resulting thrust. Observational data didn't show clear evidence of rotation state changes, but the monitoring was not continuous, and subtle variations could have been missed. Future modelling efforts aimed to incorporate detailed simulations of tidal rotational coupling, but these studies required better constraints on the object's mass distribution and internal structure information that was difficult to obtain from ground-based observations alone. Comparison with Oumuamua and 2I, Borisov, the discovery of 3IATLAS marked only the third confirmed detection of an interstellar object passing through our solar system. and comparisons with its predecessors 1I, Oumuamua, and 2I, Borisov, were inevitable. Each of these visitors offered unique insights, yet they differed dramatically in behavior and appearance, raising questions about the diversity of interstellar populations. Oumuamua, discovered in October 2017, was the first recognized interstellar object and remains one of the most puzzling. Its initial detection by the Pan-STARRS survey in Hawaii revealed an object with a highly elongated shape, estimated to have an axis ratio of at least 5:1, and possibly as extreme as 10:1. Photometric observations showed dramatic brightness variations consistent with a tumbling, cigar-shaped or pancake-shaped body. Like 3IATLAS, Oumuamua exhibited unexplained acceleration as it moved away from the Sun, deviating from its predicted trajectory in a way that couldn't be explained by gravity alone. The acceleration of Oumuamua sparked intense debate. No coma or tail was detected despite sensitive searches, ruling out conventional cometary outgassing of water vapor. Various hypotheses emerged, ranging from outgassing of exotic ices like hydrogen or nitrogen to more speculative ideas involving artificial origins. The consensus eventually settled on a natural explanation involving hydrogen outgassing from irradiated ices, though direct evidence remained elusive. The object's extreme shape and rapid rotation added to its mystique, and it departed the solar system before detailed follow-up observations could be conducted. 2I, Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, presented a stark contrast. This object looked and behaved exactly like a solar system comet. It displayed a bright, well-defined coma and a tail extending hundreds of thousands of kilometers. Spectroscopic observations detected water vapor, carbon monoxide, and cyanide, typical cometary volatiles. Its trajectory followed gravitational predictions precisely, with no anomalous acceleration. Borisov's nucleus was estimated to be about 1 kilometer in diameter, and its composition appeared dominated by water ice mixed with dust and silicates. It was, in every measurable way, unremarkable, a comet from another star that acted just like the comets native to our own solar system. 3IATLAS fell somewhere between these two extremes. Like Oumuamua, it showed unexplained acceleration and lacked a visible coma despite being warm enough for water ice to sublimate. Like Borisov, it appeared to be an icy body rather than a rocky one, based on its reddish colour and inferred composition. But unlike either predecessor, 3IATLAS's acceleration persisted over a longer observational period, allowing for more detailed trajectory analysis. The differences among these three objects suggest that interstellar space harbours a diverse population of small bodies, just as the solar system does. In our own planetary system, comets range from the icy, volatile-rich objects of the Kuiper Belt to the rocky, depleted nuclei that have lost most of their ice through repeated passages near the Sunday. Some comets are pristine remnants from the solar system's formation, while others have been heavily processed by radiation, collisions, and gravitational interactions. It stands to reason that interstellar objects would display similar diversity. One key question is whether the differences are intrinsic to the object's origins or the result of their journeys through space. Oumuamua and 3IATLAS may have spent millions or billions of years drifting through the interstellar medium, exposed to cosmic rays, ultraviolet radiation from distant stars, and impacts from interstellar dust. This exposure could alter their surface composition, creating refractory crusts that mask underlying ices. Borisov, by contrast, might have been ejected from its parent system more recently, retaining a fresher, more pristine composition. Alternatively, the objects may have formed in different regions of their parent protoplanetary disks. Borisov could have originated from a cold, outer region rich in water, ice and volatiles, similar to our own Kuiper belt. Oumuamua and 3IATLAS might have formed closer to their parent stars, in regions where water ice was less abundant, but other volatiles like carbon monoxide or nitrogen were present. Or they could have formed in environments with different chemical abundances altogether, reflecting variations in stellar metallicity or disk composition. The acceleration anomaly shared by Oumuamua and 3IATLAS, but absent in Borisov, is particularly intriguing. If hydrogen outgassing is indeed responsible, it implies that these two objects possess a component likely hydrogen clathrates that Borisov lacked. The presence or absence of this component could be tied to formation conditions such as temperature, pressure, and the availability of molecular hydrogen during the accretion phase. Understanding these conditions requires modelling protoplanetary disks around different types of stars and determining where in those disks hydrogen clathrates could form and remain stable. Another possibility is that the anomaly is related to the object's thermal histories. Oumuamua and 3IATLAS may have undergone processing events such as close stellar encounters, supernova shocks, or collisions that altered their internal structures in ways that promote hydrogen retention. Borisov, lacking such a history, remained a normal comet. Testing this hypothesis would require observing many more interstellar objects to determine whether the anomaly is common or rare. The challenge of predicting interstellar visitor behavior. Interstellar objects present a unique challenge for astronomers. They arrive unannounced, move quickly, and depart forever. Unlike comets and asteroids native to the solar system, which follow predictable orbits and can be studied over multiple apparitions, interstellar visitors offer only a single, fleeting opportunity for observation. Once they're gone, they're gone. There are no second chances to refine measurements or test hypotheses. This one-shot nature makes predicting their behavior exceptionally difficult. The prediction problem begins with detection. Current sky survey systems scan only a fraction of the sky at any given time, and they're optimized to find objects on bound orbits rather than hyperbolic trajectories. Most interstellar objects likely pass through undetected simply because they're too faint or because they happen to cross regions that aren't being monitored. The ones we do detect are typically discovered only after they've already passed perihelion, when they're closest to the Sun and brightest. By that point, much of their approach phase, when they're warming up and potentially beginning to outgas, has already occurred unobserved. This late detection severely limits our ability to track changes in behavior. Ideally, astronomers would observe an interstellar object continuously from the moment it enters the inner solar system until it departs, capturing its thermal evolution, rotation state changes, and any outgassing activity from start to finish. In practice, coverage is sparse, with observations separated by hours or days, and many critical phases go unseen. For 3IATLAS, the acceleration anomaly was detected only after several weeks of observations, when enough data points had accumulated to reveal the deviation from predictions. By then, the object was already heading back out of the solar system. Predicting an interstellar object's trajectory requires knowing not just its position and velocity, but also any non-gravitational forces acting on it. For solar system comets, these forces are well characterized thanks to decades of study. Astronomers have developed empirical models that relate outgassing activity to heliocentric distance, surface temperature, and volatile composition. These models allow for reasonably accurate long-term predictions even for active comets with complex outgassing patterns. But interstellar objects don't necessarily follow the same rules. Their compositions may differ from solar system bodies, having formed under different conditions around different stars. Their thermal histories, millions or billions of years in interstellar space, could alter their surface properties in ways that affect how they respond to solar heating. And their outgassing, if it occurs, might involve volatiles that are rare or absent in solar system comets, making established models inapplicable. The case of 3IATLAS illustrates this problem vividly. Early trajectory predictions, based on the assumption that the object would behave like a typical inactive asteroid, proved incorrect once the acceleration became apparent. Revised models that incorporated cometary outgassing also failed to match observations because no coma was detected, and the magnitude of the acceleration didn't align with standard outgassing rates for common volatiles like water or carbon dioxide. To improve predictions, astronomers need more data and more interstellar objects to study. Each new detection adds to the sample size, revealing patterns and trends that can inform theoretical models. If future interstellar objects all exhibit anomalous acceleration, it would suggest a common underlying mechanism, such as hydrogen outgassing. If some accelerate and others don't, it would indicate diversity in composition or structure. The challenge is that interstellar objects are rare, with only a handful discovered so far, and it may take years or decades to build a statistically meaningful sample. Another complicating factor is the speed at which these objects move. 3IATLAS was travelling at over 40 kilometers per second relative to the Sun, meaning it crossed the inner solar system in a matter of weeks. Telescopes had to react quickly to capture observations before the object faded from view. Coordination among observatories worldwide was essential, but even with excellent cooperation, gaps in coverage were inevitable due to weather, scheduling conflicts, and the limited availability of the most powerful instruments. Spacecraft missions offer a potential solution, but they face enormous technical challenges. Designing a probe that can intercept a fast-moving interstellar object on short notice requires propulsion systems far beyond current capabilities. The object's hyperbolic trajectory means there's no opportunity for a leisurely rendezvous any mission would need to execute a high-speed flyby, gathering data in mere minutes or hours. Concepts for interstellar interceptor missions have been proposed, involving spacecraft on standby that could be launched rapidly once a target is detected, but these remain theoretical. What interstellar objects tell us about planetary formation? Every star begins its life surrounded by a disk of gas and dust, a protoplanetary disk. Within these disks, planets form through the gradual accumulation of material, a process that takes millions of years. But not all material ends up in planets. Some is ejected, flung out of the system by gravitational interactions, dynamical instabilities, or close encounters with newly formed giant planets. These ejected fragments become interstellar objects, drifting through the galaxy until they chance upon another star system, sometimes ours. Studying interstellar objects like 3IATLAS offers a rare glimpse into the planetary formation processes of other star systems. Each visitor carries information about the conditions in its birth system, the temperature and pressure in the protoplanetary disk, the availability of different elements, the timing of planet formation, and the dynamics that led to its ejection. In a sense, interstellar objects are messengers from distant worlds, bearing clues about environments we could never reach directly. One of the key insights is compositional diversity. The three confirmed interstellar objects, Oumuamua, Borisov, and 3IATLAS, differ markedly in appearance and behavior, suggesting they formed under varying conditions. Borisov, with its water-rich cometary composition, likely originated in the cold outer regions of a planetary system, beyond the snow line, where water ice can condense. This is similar to our own Kuiper belt, or Oort cloud, reservoirs of icy bodies left over from the solar system's formation. Borisov's normalcy suggests that the processes shaping comets in other systems are much like those in ours. Oumuamua and 3IATLAS, however, are more enigmatic. Their lack of visible outgassing, despite being warm enough for water sublimation, suggests they either lost their volatile ices over time or formed in regions where water was less abundant. If hydrogen clathrates are indeed responsible for their anomalous acceleration, it implies that molecular hydrogen was incorporated during their formation, a scenario that requires specific conditions. Hydrogen clathrates form when water ice traps hydrogen molecules in its lattice, but this only happens at very low temperatures and in environments where hydrogen is abundant. Such conditions might exist in the outer edges of protoplanetary disks or in cold molecular clouds. The discovery of objects with hydrogen-rich compositions would have profound implications for our understanding of planet formation. In our solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, contain vast amounts of hydrogen and helium captured from the protoplanetary disk. But smaller bodies, like comets and asteroids, are generally depleted in hydrogen because it escapes easily from low-gravity environments. If interstellar objects like Oumuamua and 3IATLAS retained significant hydrogen, it suggests they formed in unusual environments or through processes that efficiently trapped light gases. Another possibility is that some interstellar objects originate not from protoplanetary disks, but from later stages of planetary system evolution. During the chaotic phase of planet migration, when giant planets move inward or outward due to gravitational interactions with the disk or with each other, large numbers of small bodies can be scattered or ejected. These bodies might come from the inner regions of a system where rocky material dominates, or from outer regions where ices are more common. The mix of materials in an interstellar object could reveal which region it came from and when in the system's history it was ejected. Ejection itself is a violent process. When a small body has a close encounter with a planet, it can gain enough velocity to escape the star's gravitational pull entirely, becoming unbound. Simulations of planetary system evolution show that this happens frequently, especially in systems with massive planets on eccentric or inclined orbits. Some estimates suggest that for every rocky planet that forms, hundreds or thousands of smaller bodies are ejected into interstellar space. Over the billions of years of a galaxy's history, this process populates the interstellar medium with a vast population of wandering objects, some rocky, some icy, some a mix of both. The abundance of interstellar objects passing through the solar system can, in turn, constrain models of planetary formation. By observing how many interstellar visitors we detect per year and extrapolating to the total population, astronomers can estimate the ejection rate averaged over all planetary systems in the galaxy. These estimates feed into theoretical models, helping refine our understanding of how planetary systems form, evolve, and distribute material. Interstellar objects also offer clues about the chemistry of their parent systems. Spectroscopic observations, though limited, can reveal the presence of specific molecules or minerals that indicate the chemical environment during formation. For example, the detection of organic compounds on 3IATLAS's surface suggests exposure to UV radiation and cosmic rays, but the initial composition of those organics, whether they formed in the protoplanetary disk or later in interstellar space, remains uncertain. Future observations with more powerful spectrographs could identify isotopic ratios, which are sensitive indicators of formation temperature and the types of chemical reactions that occurred. The diversity of interstellar objects mirrors the diversity of exoplanetary systems. Thousands of exoplanets have been discovered around other stars, and they exhibit a bewildering variety of sizes, compositions, and orbital architectures, many unlike anything in our solar system. Hot Jupiters, super-Earths, and mini-Neptunes have no counterparts here, suggesting that planet formation proceeds differently under different conditions. Interstellar objects, as the leftover fragments of those systems, reflect that diversity. Studying them is, in effect, studying exoplanetary systems from a new angle. The role of molecular clouds in shaping interstellar objects. Before interstellar objects like 3IATLAS were ever incorporated into protoplanetary disks, they, or at least the material from which they formed, existed in molecular clouds. These vast, cold regions of space are the birthplaces of stars and planetary systems, and they profoundly influence the properties of any bodies that form within them. Understanding molecular clouds is essential to understanding the origins and behaviors of interstellar visitors. Molecular clouds are dense concentrations of gas and dust scattered throughout galaxies. They consist primarily of molecular hydrogen, with trace amounts of heavier molecules like carbon monoxide, ammonia, and complex organic compounds. Temperatures within molecular clouds hover just above absolute zero, typically 10 to 20 Kelvin, making them some of the coldest environments in the universe. At these temperatures, molecules move slowly, and chemical reactions proceed at glacial rates, allowing fragile compounds to survive that would quickly break apart in warmer regions. When a region within a molecular cloud becomes dense enough, gravity takes over, and the cloud begins to collapse. The material falls inward, heating up, and eventually forming a protostar at the center. Around the protostar, a rotating disk of gas and dust forms the protoplanetary disk, from which planets and smaller bodies will eventually coalesce. The composition of this disk is determined largely by the chemistry of the parent molecular cloud, which in turn depends on factors like temperature, density, radiation from nearby stars, and the abundance of heavy elements. For objects like 3IATLAS, their formation within a molecular cloud environment may have left lasting imprints on their composition. If the cloud was particularly cold and shielded from external radiation, it could have retained high abundances of volatile ices like carbon monoxide, nitrogen, and even molecular hydrogen. These ices would then be incorporated into the grains and particles that eventually aggregated to form comets and planetesimals. As these small bodies grew through collisions and accretion, they captured the chemical signature of the cloud, a signature that might persist even after the object was ejected from its birth system. One of the most intriguing aspects of molecular cloud chemistry is the formation of complex organic molecules. Despite the frigid temperatures, molecular clouds host a surprisingly rich chemistry. Simple molecules like water, methane, and ammonia form on the surfaces of dust grains, where they can stick together and react slowly. Over time, these reactions produce more complex species, including alcohols, aldehydes, and even amino acids, the building blocks of life. Infrared observations of molecular clouds have detected dozens of different organic molecules, some with structures as complex as 10 or more atoms. If 3IATLAS formed in such an environment, its interior could harbour complex organics inherited from the molecular cloud. These compounds would be locked inside the icy matrix, protected from destruction by cosmic rays and UV radiation. When the object later entered a planetary system and was heated by a star, these organics could sublimate and escape into space, a process that might contribute to the observed acceleration. The reddish colour of 3I, Atlas's surface, attributed to organic tholins, supports the idea that it contains or once contained organic-rich material. Another important factor is the metallicity of the molecular cloud, the abundance of elements heavier than hydrogen and helium. Stars form from material enriched by previous generations of stars that exploded as supernovae, scattering heavy elements into space. The more supernovae that have occurred in a region, the higher the metallicity of the molecular cloud and the protoplanetary disks that form within it. Metallicity affects planet formation, influencing the size and composition of planets and the efficiency with which dust grains coagulate. It also affects the chemistry available for forming comets and asteroids. If 3IATLAS originated from a system with different metallicity than our solar system, it might contain unusual ratios of elements or minerals not commonly found here. Detecting such anomalies would require detailed spectroscopic analysis, ideally with high-resolution instruments capable of identifying specific isotopes. Isotopic ratios are particularly revealing because they reflect nuclear processes in the star or supernova that produced the material, providing a kind of fingerprint of the object's origin. The age of the molecular cloud also matters. Clouds in the early universe, shortly after the first stars formed, had very low metallicity because few heavy elements existed yet. Objects forming from such clouds, called population 3 or very metal-poor objects, would be composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. By contrast, molecular clouds forming today are enriched with the products of billions of years of stellar nucleosynthesis. Interstellar objects like 3IATLAS could, in principle, come from systems of various ages, and their compositions would reflect that history, the frequency of interstellar objects in the solar system. How common are interstellar visitors like 3IATLAS? The question is crucial for understanding galactic dynamics, the efficiency of planetary formation, and even the potential for panspermia, the hypothesis that life could spread between star systems via interstellar objects. Estimating the frequency of these objects requires combining observational data with theoretical models of ejection rates and population densities. When Oumuamua was discovered in 2017, it was immediately clear that interstellar objects passing through the solar system couldn't be extremely rare. The mere fact that we detected one, given the limited sky coverage of survey telescopes, suggested that many more must exist. Researchers quickly set about estimating the population. Based on Oumuamua's discovery circumstances and the survey's detection efficiency, they calculated that roughly one interstellar object larger than 100 meters passes within Earth's orbit per year. Smaller objects would be more numerous, but harder to detect. The discovery of 2I, Borisov, in 2019 refined these estimates. With 2 detections in just a few years, statistical models could be updated to account for the observed rate. The revised estimates suggested that at any given time, there might be thousands of interstellar objects within the orbit of Neptune, though most are too small and faint to detect with current technology. Scaling up to the entire solar system, the number could be in the tens of thousands or more. 3IATLAS's discovery in 2024 further confirmed that interstellar objects are not anomalies, but a regular feature of our cosmic neighbourhood. With 3 confirmed detections over roughly 7 years, and noting that many objects likely went unnoticed due to observational gaps, the inferred population density is consistent with theoretical predictions. Models of planet formation and ejection suggest that for every star in the galaxy, millions or billions of small bodies are ejected over the star's lifetime. Given the roughly 200 billion stars in the Milky Way, the interstellar medium should be teeming with wandering objects. Extrapolating these numbers galaxy-wide leads to staggering figures. If each star system ejects, on average, 10 billion objects, ranging from meter-sized rocks to kilometer-sized comets, over its history, and there are 200 billion stars, then the Milky Way contains roughly 1021 interstellar objects, spread over the galaxy's volume roughly 10-12 cubic light-years. That works out to about 1 billion objects per cubic light-year. Of course, most of these are tiny, and only the largest would ever be detectable. These population estimates have implications for the possibility of panspermia. If interstellar objects are numerous and some originate from systems where life exists, they could potentially carry microorganisms or at least organic molecules between star systems. While the harsh conditions of interstellar space, intense radiation, extreme cold, and near total vacuum make survival challenging, laboratory experiments have shown that certain microbes can endure such environments if protected inside ice or rock. Whether life actually spreads this way remains speculative, but the sheer number of interstellar objects makes the scenario at least plausible. The frequency of interstellar objects also affects planetary systems. Over billions of years, a star system will not only eject objects, but also capture or be impacted by visitors from elsewhere. While capture is difficult, requiring the object to lose enough energy to become gravitationally bound impacts are possible. A large interstellar object striking a planet could deliver water, organic molecules, or even trigger mass extinction events. Earth itself may have been struck by interstellar impactors in the distant past, though identifying such events in the geological record is nearly impossible without isotopic signatures or other clear markers. The detection rate of interstellar objects is expected to increase dramatically in the coming years. Next-generation survey telescopes, such as the Vera Rubin Observatory, formerly LSST, will scan the entire visible sky every few nights with unprecedented sensitivity. Simulations predict that Rubin could detect dozens of interstellar objects per year, building a large statistical sample that will reveal the true diversity and abundance of these cosmic wanderers. With more detections, patterns will emerge. Perhaps certain types are more common, or trajectories cluster in specific regions of the sky, hinting at large-scale galactic structure effects. Future observations and missions. The challenges posed by 3IATLAS underscore the need for better observational capabilities and, ultimately, dedicated missions to study interstellar objects up close. Ground-based telescopes have provided invaluable data, but they are limited by Earth's atmosphere, weather, observing schedules, and the faintness of these distant visitors. Space-based assets and eventual spacecraft missions will be essential for unraveling the mysteries these objects present. One immediate priority is improving sky survey coverage. Current surveys, while impressive, still miss large swaths of sky and can only detect relatively bright objects. The Vera Rubin Observatory, set to begin full operations soon, will revolutionize this field. Its 8.4-meter mirror and massive camera will image the entire visible sky every few nights, detecting objects far fainter than current surveys can reach. Rubin's rapid cadence will catch interstellar objects early, soon after they enter the inner solar system, allowing for prolonged monitoring and better characterization. With earlier detections, astronomers will have more time to coordinate follow-up observations. High-resolution imaging can reveal surface features, rotation states, and signs of fragmentation. Spectroscopy can search for emission lines from outgassing, even if faint, and identify specific volatiles. Polarimetry and infrared photometry can constrain surface textures and thermal properties. The more data gathered early in an object's passage, the better the trajectory predictions and the deeper the scientific insights. Space-based telescopes offer advantages that ground-based instruments cannot match. Observatories like the James Webb Space Telescope, JWST, can perform infrared spectroscopy with exquisite sensitivity, detecting molecules and ices on the surfaces of interstellar objects that are invisible to ground-based instruments. JWST's position in space eliminates atmospheric interference, allowing it to observe continuously without weather delays or daylight interruptions. While JWST's time is precious and heavily subscribed, interstellar object detections could justify directors' discretionary time for rapid response observations. Another promising avenue is radio astronomy. If interstellar objects outgas molecules like water, carbon monoxide, or methanol, these can be detected through their characteristic radio emissions. The Atacama Large Millimeter, Sub-Millimeter Array, ALMA, with its exceptional sensitivity, could detect even faint outgassing that produces no visible coma. Radio observations also have the advantage of being unaffected by the object's distance or illumination conditions, as they rely on molecular emission rather than reflected sunlight. But the ultimate goal is a spacecraft mission, a probe that can rendezvous with an interstellar object and study it up close. Several mission concepts have been proposed over the years, each facing significant technical challenges. The primary difficulty is the speed of these objects. Moving at tens of kilometers per second relative to the Sun, they traverse the inner solar system in weeks, leaving little time to prepare and launch a spacecraft. Even if a mission were ready on standby, reaching an interstellar object would require enormous delta V, the change in velocity far exceeding conventional propulsion capabilities. One concept, called the Interstellar Interceptor, envisions a spacecraft pre-positioned in space, ready for rapid deployment once a target is detected. The spacecraft would use a powerful kick stage to accelerate onto an intercept trajectory, then coast to a high-speed flyby, gathering data in the brief minutes or hours when the object is within range. Instruments would include high-resolution cameras, spectrometers, magnetometers, and dust detectors. The spacecraft might even carry a penetrator, a small probe designed to impact the object and analyze the ejected material, or a sample return capsule, though returning samples from an interstellar object is extraordinarily difficult. Another approach is to position spacecraft in heliocentric orbits far from Earth, strategically located to intercept objects as they pass through the outer solar system. This would allow longer interaction times and reduce the delta V requirements, though it would require predicting the object's trajectory far in advance, a challenge given the trajectory uncertainties inherent in interstellar objects. Despite the challenges, mission studies continue. The European Space Agency's Comet Interceptor mission, scheduled for launch in the next decade, is designed to target a pristine comet or possibly an interstellar object, using a mothership and deployable probes to study the target from multiple angles. While primarily aimed at long-period comets from the Oort cloud, its flexible design could be adapted to intercept an interstellar visitor if one is detected at the right time. In the longer term, advances in propulsion technology, such as solar sails, ion drives, or even fusion-based systems, could make interstellar object missions more feasible. A solar sail, for instance, could use the pressure of sunlight to accelerate rapidly without carrying heavy fuel, potentially reaching velocities high enough to catch up with an interstellar object. Concepts for such missions are being actively developed by groups like the Planetary Society and various national space agencies. The implications for SETI and technosignatures. Interstellar objects, by their very nature, connect different star systems. they cross the vast gulfs of space, bearing information and potentially material from their origins to new destinations. This has sparked interest not just among planetary scientists, but also among researchers involved in the search for extraterrestrial intelligence, SETI. Could interstellar objects serve as carriers of technosignatures, evidence of intelligent civilizations? The question gained prominence after Oumuamua's discovery, when its unusual shape and unexplained acceleration led some to speculate about artificial origins. Theoretical physicist Avi Loeb of Harvard University notably proposed that Oumuamua could be a light sail, a thin, reflective sheet propelled by starlight sent by an advanced civilization. The idea was controversial and met with skepticism from most scientists who favored natural explanations. But it highlighted a broader point. Interstellar objects are difficult to characterize with certainty, and exotic hypotheses, while unlikely, cannot be dismissed without thorough investigation. For 3IATLAS, the anomalous acceleration once again raises the question: if natural explanations like hydrogen outgassing prove inadequate, what alternatives remain? One speculative possibility is that the object is not entirely natural, that it incorporates some form of technology, whether as a probe, a derelict spacecraft, or even an artifact from a long-extinct civilization. This is not to say such scenarios are likely. They are not. But the scientific method requires considering all hypotheses consistent with the data, no matter how improbable, and then testing them rigorously. What would constitute evidence of technology? For an object like 3IATLAS, several signatures might be revealing. Anomalous radio emissions, structured signals that cannot be explained by natural processes would be a strong indicator. Highly reflective surfaces inconsistent with natural materials could suggest artificial construction. Trajectory changes that correlate with specific orientations or times, implying active control, would be suspicious. None of these have been observed in 3IATLAS, but the searches have been limited. SETI researchers have pointed out that interstellar objects offer a potential means of interstellar communication or exploration. Rather than transmitting radio signals across light years of space, an advanced civilization might send physical probes, self-replicating machines that travel from star to star, gathering information and possibly even making contact with emerging intelligences. Such probes would be essentially indistinguishable from natural interstellar objects unless examined closely. The concept, known as von Neumann probes after mathematician John von Neumann, has been explored extensively in theoretical studies. If such probes exist, they would likely outnumber naturally occurring interstellar objects given enough time and a sufficiently long-lived civilization. A single civilization launching probes over millions of years could populate an entire galaxy with billions of exploratory machines. Detecting them would require careful screening of interstellar objects, looking for subtle anomalies that betray artificial origin. The Breakthrough Listen initiative, funded by entrepreneur Yuri Milner, has undertaken just such searches. When Oumuamua was discovered, Breakthrough Listen pointed radio telescopes at the object, searching for signals across a wide range of frequencies. None were detected, placing strong limits on any radio transmissions. Similar observations could be conducted for 3IATLAS, though the object's faintness and rapid motion pose challenges. Another approach is to look for physical anomalies. A spacecraft or probe would likely have a different mass-to-area ratio than a natural object, affecting how it responds to radiation pressure and other forces. Its surface might have unusual thermal properties, reflecting or absorbing light in ways inconsistent with rock or ice. Its trajectory might show course corrections, small, deliberate changes, inconsistent with outgassing or gravitational perturbations. None of these signatures have been found in any confirmed interstellar object to date, which strongly suggests that Oumuamua, Borisov, and 3IATLAS are natural bodies. But the absence of evidence is not evidence of absence, especially given the limited data. As detection rates increase and observational capabilities improve, the possibility of eventually encountering an artificial interstellar object, however remote, remains within the realm of scientific consideration. There is also the question of panspermia, not just of microbial life, but of technological artifacts. If intelligent civilizations arise and then go extinct, their creations might persist, drifting through space long after their makers are gone. Ancient probes, derelict spacecraft, or even deliberate time capsules could be among the interstellar objects passing through our solar system. Identifying such artifacts would be one of the most profound discoveries in human history, reshaping our understanding of intelligence, civilization, and our place in the cosmos. The mystery deepens. Months after its discovery, 3IATLAS remains an enigma. Despite extensive observations, detailed modelling, and comparisons with other interstellar objects, the cause of its anomalous acceleration has not been definitively identified. The mystery deepens with every new piece of data, each measurement adding complexity rather than clarity. Hydrogen outgassing remains the leading hypothesis, but it is far from confirmed. The mechanism is plausible, the physics sound, but direct evidence is lacking. No hydrogen emission has been detected. No thermal signatures unambiguously point to sublimating clathrates. And the magnitude of the acceleration still requires fine-tuning of parameters. It is a solution that fits, but not comfortably. Alternative explanations continue to circulate. Some researchers argue that the object's internal structure, perhaps unusually porous or fractured, allows for more efficient heat transfer, triggering deeper sublimation than thermal models predict. Others suggest that the surface is covered with a volatile rich layer that sublimates rapidly but produces gases too faint or too optically thin to generate a visible coma. Still others point to unexplored volatiles, molecules that might be common in interstellar environments but rare in the solar system, with sublimation properties that don't match the standard cometary library. There is also the possibility that multiple mechanisms are at work simultaneously. Perhaps 3IATLAS is outgassing hydrogen and experiencing Yarkovsky-like thermal forces and undergoing subtle tidal effects, all contributing to the observed acceleration. Complex systems often defy simple explanations, and interstellar objects formed in distant environments and processed by millions of years in space are nothing if not complex. The lack of a visible coma remains one of the most puzzling aspects. For any substantial outgassing to occur, gas must escape the object's surface at rates high enough to generate the observed thrust. Yet that gas, once released, should scatter sunlight and form at least a faint coma detectable by sensitive instruments. The fact that none has been seen suggests either that the gas is extremely transparent, like pure hydrogen or nitrogen, or that it's being released in very collimated jets that don't disperse into a diffuse cloud. Collimated jets are known to occur on comets, where gas escapes through narrow fissures or vents rather than uniformly across the surface. These jets can produce significant thrust without creating an obvious coma, especially if they're oriented in specific directions. If 3IATLAS has active vents located near its poles or along its rotation axis, the resulting jets could be difficult to detect from Earth, particularly if they point away from us. Another unresolved issue is the persistence of the acceleration. Typically, cometary outgassing is strongest near perihelion and declines rapidly as the object moves away from the Sunday. Yet 3IATLAS's acceleration continued well past perihelion, suggesting either that the heat source is not purely solar or that the object has significant thermal inertia, storing heat and releasing it gradually over time. Some models invoke internal heat sources, perhaps radioactive decay or residual warmth from tidal heating, but these are speculative. The object's composition remains poorly constrained. Spectroscopy has revealed little beyond a reddish colour and the likely presence of organics. No strong absorption features have been detected that would indicate specific ices or minerals. This featurelessness is itself informative. It suggests a surface covered with a dark, carbon-rich crust or regolith that masks any underlying composition. But without knowing what lies beneath, predictions about behaviour remain uncertain. As 3IATLAS fades from view, moving beyond the reach of even the most powerful telescopes, the opportunity for further direct observation dwindles. The object will continue its journey back into interstellar space, becoming once again a wanderer among the stars. For astronomers, it leaves behind a trail of unanswered questions and a humbling reminder of how much remains unknown about the cosmos. Lessons from 3IATLAS. The story of 3IATLAS, though still unfolding, offers valuable lessons for astronomy and planetary science. It reveals the limits of current understanding, highlights gaps in observational capabilities, and underscores the importance of humility when confronting the unknown. First, the discovery demonstrates that interstellar objects are not merely curiosities, but key targets for advancing planetary science. Each one provides a unique data point, a sample from another star system delivered to our doorstep. Collectively, they offer insights into the diversity of planetary formation processes, the chemistry of interstellar space, and the dynamics of galactic evolution. As detection rates increase, the field of interstellar object studies will transition from the anecdotal to the statistical, enabling robust comparisons and trend analyses. Second, 3IATLAS shows that even well-established models can fail when applied to unfamiliar contexts. Cometary physics, refined over centuries of study, could not predict the object's behavior. This is not a failure of science, but a reminder that models are built on assumptions that may not hold for objects formed in different environments. Expanding those models to accommodate interstellar visitors will require new data, new experiments, and perhaps entirely new theoretical frameworks. Third, the case highlights the need for rapid response observational infrastructure. Interstellar objects move quickly and offer limited windows for study. Coordinating global telescope networks, prioritizing targets, and developing flexible scheduling systems will be essential for maximizing scientific return. Automated alert systems, like those used by ATLAS and other survey projects, are crucial for early detection, but follow-up requires human judgment and collaboration. Fourth, 3IATLAS illustrates the value of interdisciplinary approaches. Understanding its behavior requires expertise in orbital mechanics, spectroscopy, thermal modeling, chemistry, and even SETI. No single field holds all the answers. Collaborative efforts that bring together diverse perspectives are more likely to uncover the truth. Finally, the object serves as a reminder of the vastness of what we do not know. Despite millennia of stargazing and centuries of scientific investigation, the universe still surprises us. Objects like 3IATLAS arrive unannounced, challenge our theories, and depart without revealing all their secrets. This is the nature of exploration, each answer leading to new questions, each discovery opening new frontiers. As we look to the future, the lessons of 3IATLAS will guide the next generation of interstellar object studies. Better telescopes will detect more objects, Spacecraft missions will eventually visit them, and our understanding will deepen. But for now, the mystery remains. Why did 3IATLAS accelerate toward the Sun? What drove its unexpected motion? The answers are out there, drifting through the dark, waiting for the next visitor to tell their story. The physics of non-gravitational forces in deep space. When an object moves through the solar system, its trajectory is governed primarily by gravity, the pull of the Sun, the tug of planets, and the influence of every massive body in its vicinity. Newton's laws describe these motions with remarkable precision, allowing astronomers to predict positions years or even centuries into the future. But gravity isn't the only force at play. A suite of subtle, non-gravitational forces can alter trajectories in ways that become significant over time, and for objects like 3IATLAS, these forces may hold the key to understanding its anomalous behavior. Non-gravitational forces fall into several categories, each arising from different physical mechanisms. Solar radiation pressure is perhaps the most straightforward. Photons from the Sun carry momentum, and when they strike an object, they transfer that momentum, exerting a tiny push. For small particles, dust grains and micrometeoroids, this force can dominate over gravity, blowing material out of the solar system entirely. For larger objects, the effect is much weaker, but still measurable over long timescales. The magnitude of radiation pressure depends on the object's cross-sectional area, reflectivity, and mass. A highly reflective, low-mass object experiences stronger acceleration than a dark, massive one. For 3IATLAS, with an estimated diameter of several hundred meters and unknown but likely low albedo, radiation pressure alone produces an acceleration far too small to explain observations. Calculations show that even under optimistic assumptions, radiation pressure accounts for less than 1% of the observed anomaly. The Yarkovsky effect adds a thermal twist to radiation pressure. As a rotating object absorbs sunlight, it heats up. Hours later, as the heated surface rotates away from the Sun, it re-radiates that energy as infrared light. Because the afternoon side, the side that was recently illuminated, is warmer than the morning side, more thermal photons are emitted in one direction than the other. This creates a net thrust. For asteroids in the main belt, the Yarkovsky effect can shift orbits by kilometers or more over millions of years, a process that gradually delivers asteroids into resonances with Jupiter and ultimately toward Earth-crossing orbits. The strength of the Yarkovsky effect depends on rotation rate, thermal inertia, surface roughness, and composition. Rocky asteroids with slow rotation and low thermal conductivity experience stronger effects than icy bodies that rotate rapidly. For 3IATLAS, with its 8-hour rotation period and presumed icy composition, the Yarkovsky acceleration should be modest, perhaps a few times 10, -8 meters per second squared. This is, again, far below the observed acceleration of roughly 4.5 millimeters per second squared. Outgassing represents a much stronger non-gravitational force. When volatile ices sublimate, the escaping gas carries momentum, creating a rocket-like thrust. The magnitude depends on the outgassing rate, the molecular weight of the gas, and the geometry of the emission. Water vapor, the dominant volatile in most solar system comets, produces thrust efficiently because it has moderate molecular weight and sublimates vigorously near the sunday. Carbon monoxide and carbon dioxide, lighter and more volatile, generate even stronger thrust per unit mass. The challenge with 3IATLAS is reconciling the required outgassing rate with the lack of observable activity. To produce the observed acceleration, the object would need to lose several kilograms of material per second, a rate easily sufficient to create a detectable coma if the gas were water vapor or carbon dioxide. The absence of a coma suggests either that the outgassing is highly asymmetric, confined to narrow jets that don't disperse into a diffuse cloud, or that the escaping gas is exceptionally transparent, like molecular hydrogen. Hydrogen outgassing, as discussed in earlier chapters, remains the most viable explanation because molecular hydrogen doesn't scatter sunlight effectively. Even large outgassing rates produce no visible coma. The gas simply streams away invisibly, carrying momentum and accelerating the object. If 3IATLAS contains hydrogen, clathrates, ices with trapped hydrogen molecules, solar heating could destabilize these structures, releasing hydrogen and producing the observed thrust. But there's another class of non-gravitational forces that operates on even subtler levels: electromagnetic interactions. Interstellar space is not empty. It contains charged particles, magnetic fields, and low-frequency electromagnetic radiation. Objects moving through this medium can experience drag, much like a spacecraft moving through Earth's upper atmosphere. Charged dust grains on an object's surface can interact with the interplanetary magnetic field, producing forces that, while tiny, accumulate over time. For 3IATLAS, electromagnetic forces are almost certainly negligible. The object is electrically neutral overall, and any surface charging would be minimal. The interplanetary magnetic field is weak, and drag from the solar wind, the stream of charged particles flowing outward from the Sun, affects only the smallest, lightest particles. Calculations confirm that electromagnetic forces contribute less than 1/billionth of the required acceleration. There is also the matter of tidal forces, though these operate differently than the other mechanisms. When an object passes close to a massive body, differential gravity stretches it, potentially causing internal friction and heating. For 3IATLAS, the closest approach to the Sun occurred at 0.8 astronomical units, and the closest planetary encounter was with Jupiter at several AU. Neither interaction produced significant tidal stress. Tidal heating, if it occurred at all, would have been confined to the perihelion passage and would have declined rapidly afterward. The persistence of the acceleration well past perihelion argues against tidal heating as the primary driver. Another exotic possibility involves momentum transfer from impacts with interplanetary dust. The solar system is filled with microscopic particles, remnants of comets and asteroids that drift in elliptical orbits or spiral slowly toward the Sunday. An object moving at high velocity could collide with millions of these particles, and the cumulative momentum transfer might, in principle, alter its trajectory. However, the mass of interplanetary dust is so small and the collision rate so low that this effect is entirely negligible for a body the size of 3IATLAS. One avenue that has received less attention is the role of mass loss asymmetry. If 3IATLAS is shedding mass, whether through outgassing, dust ejection, or sublimation, and that mass loss is not uniform across the surface, the resulting thrust can be significant. Imagine a comet with active regions confined to one hemisphere. As gas escapes from these regions, the object is pushed in the opposite direction. If the active regions are near the object's poles and aligned with its spin axis, the thrust can be nearly constant, independent of rotation, producing sustained acceleration in a fixed direction. Modelling such scenarios requires detailed knowledge of the object's shape, rotation state, and thermal properties, information that is largely unavailable for 3IATLAS. Researchers have constructed synthetic models, varying parameters to see which configurations can reproduce the observed trajectory. Many solutions exist, But without independent constraints, it's impossible to determine which, if any, corresponds to reality. The interplay of these forces makes predicting interstellar object behavior extraordinarily difficult. Unlike solar system comets, which have been studied for centuries and whose behaviors are well calibrated, interstellar visitors offer no historical record. Each one is a first encounter, requiring models to be built from scratch, and when the models fail, as they have for Oumuamua and now 3IATLAS, it exposes the limits of current understanding, the search for volatiles beyond water ice. Water ice dominates the composition of most comets in the solar system, but it is far from the only volatile present. Carbon monoxide, carbon dioxide, methane, ammonia, and nitrogen all play significant roles in cometary activity, and their relative abundances vary widely depending on where and when a comet formed. For interstellar objects like 3IATLAS, which may have formed in protoplanetary disks around different types of stars, the volatile inventory could differ dramatically from what we see in solar system comets. Understanding these differences is key to explaining their behavior. Water ice sublimates at temperatures above about 180 Kelvin, which corresponds to a heliocentric distance of roughly 3 astronomical units. Inside this distance, sunlight provides enough energy to drive vigorous outgassing, producing the bright Comet tails characteristic of active comets. Beyond this boundary, water ice remains frozen and comets become dormant, their activity ceasing until they venture closer to the Sun again. This behavior has been observed countless times and forms the basis of cometary science. But other volatiles sublimate at much lower temperatures. Carbon monoxide ice, for instance, begins to sublimate at around 25 Kelvin, corresponding to distances beyond 100 astronomical units. Nitrogen ice is similarly volatile, with sublimation temperatures near 35 Kelvin. These hypervolatiles can drive activity at vast distances from the Sun, far beyond where water ice would remain frozen. If 3IATLAS contains significant amounts of carbon monoxide or nitrogen, it could have been outgassing long before entering the inner solar system, and that activity could persist even as it moves outward again. Detecting hypervolatiles is difficult. Carbon monoxide and nitrogen don't produce strong emission lines in visible light, making them nearly invisible to optical telescopes. Radio and millimeter wave observations can detect them through rotational transitions of molecules, but only if the outgassing rate is high enough. For a faint, distant object like 3IATLAS, such observations push the limits of current instrumentation. Observations with ALMA, the Atacama Large Millimeter Array, were attempted during 3IATLAS's passage, searching for the characteristic emission lines of carbon monoxide at 230 and 345 GHz. The observations were challenging, requiring long integration times to achieve sufficient sensitivity. Preliminary results showed no clear detections, placing upper limits on the carbon monoxide outgassing rate. These limits were consistent with the object being inactive in carbon monoxide, or, alternatively, releasing the gas at rates below the detection threshold. Carbon dioxide is another common cometary volatile, more abundant than carbon monoxide in many solar system comets. It sublimates at temperatures around 80 Kelvin, intermediate between water and carbon monoxide, and can drive activity at heliocentric distances of 5 to 10 astronomical units. Infrared spectroscopy can detect carbon dioxide through its absorption bands at 4.27 and 2.7 microns, but again, the faintness of 3IATLAS limited the signal-to-noise ratio. Searches for carbon dioxide found no conclusive detections, though weak, tentative features appeared in some spectra. These features could not be confirmed independently, leaving the question open. Methane and ammonia, common in the outer solar system, are also candidates. Methane sublimates at temperatures around 50 Kelvin, while ammonia remains solid until temperatures exceed 150 Kelvin. Both have been detected in solar system comets through their infrared absorption features and emission lines. For 3IATLAS, searches in the near-infrared found no clear signatures of either molecule, but again, the data were noisy and weak features could easily be buried. The absence of detections doesn't necessarily mean these volatiles are absent. It could simply mean their abundances are low or their outgassing rates too faint for current instruments to resolve. Alternatively, the volatiles might be present but sequestered beneath a thick surface crust that prevents their escape. Many solar system comets exhibit such behavior, volatile-rich interiors insulated by refractory crusts that only crack and expose fresh ice during close solar passes or after impacts. There is also the possibility that 3IATLAS contains volatiles not commonly found in solar system comets. Different protoplanetary disks have different chemical inventories, determined by factors like the host star's metallicity, the disk's temperature structure, and the availability of specific molecules in the parent molecular cloud. A comet forming around a carbon-rich star, for instance, might have higher abundances of organic compounds and carbon-bearing molecules than one forming around an oxygen-rich star. Exotic ices like formaldehyde, methanol, or even more complex organics could be present. These molecules have lower vapor pressures than water ice and might sublimate gradually over long periods, contributing to a sustained, low-level outgassing that produces thrust without an obvious coma. Detecting such species requires high-resolution spectroscopy in specific wavelength ranges, often in the infrared or submillimeter, where the Earth's atmosphere is opaque and space-based observations are necessary. The James Webb Space Telescope, with its powerful infrared instruments, offers new opportunities for detecting these exotic volatiles. Its sensitivity and spectral resolution far exceed previous space telescopes, enabling the detection of weak absorption and emission features from faint, distant objects. Future interstellar objects discovered early in their passages could become priority targets for JWST, providing the detailed compositional data needed to understand their origins and behaviors. Another intriguing possibility is that the volatiles driving 3I, Atlas's acceleration, are not ices at all, but gases trapped in amorphous ice structures. Amorphous ice, unlike the familiar crystalline ice found in ice cubes and glaciers, has a disordered molecular structure that can trap small molecules like carbon dioxide, methane, and nitrogen in pockets and voids. When amorphous ice is warmed and transitions to crystalline ice, a process that occurs around 130 Kelvin, the trapped gases are suddenly released in a burst. This outburst can produce significant thrust over short timescales. Amorphous ice is thought to be common in the outer regions of protoplanetary disks, where temperatures are low and water condenses rapidly without forming ordered crystals. If 3IATLAS formed in such an environment and retained its amorphous structure through millions of years in interstellar space, solar heating during its passage through the inner solar system could trigger crystallization, releasing trapped gases. The timing would align with the observed acceleration, and the lack of a visible coma could be explained if the released gases were optically thin species like nitrogen or carbon monoxide. The fate of 3IATLAS. As 3IATLAS recedes from the Sun, climbing back up the steep gravitational well it descended months earlier, its story enters a final, quieter chapter. The object is now beyond the orbit of Mars, its brightness fading with each passing week as sunlight weakens and the distance to Earth grows. Soon, even the most powerful telescopes will lose sight of it, and 3IATLAS will return to the darkness from which it came, a wanderer bound for the abyss between stars. Unlike comets native to the solar system, which may return on predictable orbits after decades or centuries, 3IATLAS will never be seen again. Its hyperbolic trajectory ensures that it will escape the Sun's gravity entirely, accelerating toward interstellar velocities as it crosses the outer reaches of the planetary system. In a few years, it will pass beyond the orbit of Neptune. In a decade, it will traverse the Kuiper Belt, that distant realm of icy bodies marking the edge of the Sun's domain. And in a century or two, it will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium, and return to the vast, cold expanse between stars. The journey ahead is almost unimaginably long. Space between stars is not truly empty, but it is emptier than any vacuum humans can create. The density of matter in interstellar space averages about 1 atom per cubic centimetre, mostly hydrogen, with traces of helium and heavier elements. For comparison, Earth's atmosphere at sea level contains about 10-19 molecules per cubic centimetre. To move through interstellar space is to drift through the closest thing to absolute nothingness that nature allows. At its current velocity, approximately 42 kilometers per second relative to the Sun, 3IATLAS will travel 1 light-year in about 7,000 years. The nearest star system, Alpha Centauri, lies 4.37 light-years away, meaning it would take roughly 30,000 years for the object to cover that distance. But 3IATLAS is not heading toward Alpha Centauri. Its trajectory points in a different direction entirely, toward the constellation Lyra, where the bright star Vega shines. Even Vega, at 25 light-years distant, lies more than 150,000 years away at the object's current speed. Over such timescales, the concept of destination becomes almost meaningless. Stars themselves move, drifting through the galaxy on their own orbital paths around the Milky Way's center. In 150,000 years, Vega will have shifted significantly from its current position, and other stars may have moved closer to 3IATLAS's path. The object will not be heading toward any specific star, but simply outward into the general galactic disk, a tiny grain adrift in an ocean of stars. What will happen to 3IATLAS during this journey? The interstellar environment, though sparse, is not benign. Cosmic rays, high-energy particles, accelerated by supernova explosions and other violent events, constantly bombard the object's surface. Over millions of years, this radiation alters the chemical composition of surface materials, breaking apart molecules and forming new, more complex compounds. This process, called space weathering, gradually darkens and reddens surfaces, creating the spectral signatures observed on many outer solar system objects and likely on 3IATLAS itself. Micrometeorite impacts, though rare, will slowly erode the surface. Each impact vaporizes a tiny amount of material, gradually sandblasting the object and roughening its texture. Larger impacts, perhaps once every few million years, could fracture the surface or even split the object into multiple pieces. If 3IATLAS is a loosely bound rubble pile, such impacts might be particularly destructive, scattering fragments along its orbital path. The object will also experience the faint pressure of starlight from distant stars and the even fainter tug of the galactic gravitational field. These forces are negligible over human timescales, but accumulate over millions or billions of years. Slowly, imperceptibly, they will alter the object's trajectory, curving its path through the galaxy in ways impossible to predict without detailed knowledge of the galactic mass distribution, a distribution dominated by unseen dark matter. Temperature will drop dramatically as 3I Atlas moves farther from the Sunday. Already cold, the object will cool toward the temperature of the cosmic microwave background, the faint glow of radiation left over from the Big Bang, which permeates all of space at a temperature of 2.7 Kelvin. At this temperature, only a few degrees above absolute zero, all chemical and physical processes slow to a near halt. Any remaining volatiles will freeze solid, locking them in place for eons. But the story doesn't necessarily end with eternal drift. Billions of years from now, 3IATLAS may encounter another star system. If that system has planets, the object could be captured into orbit, becoming a temporary comet or asteroid within that distant solar system. Alternatively, it could pass through without capture, briefly warming in the light of a foreign sun before continuing onward. Over the tens of billions of years remaining in the universe's long future, 3IATLAS might visit dozens of star systems, an accidental ambassador from the sun to distant worlds. There is even a remote possibility that 3IATLAS could return. Gravitational interactions within the galaxy, close encounters with massive molecular clouds, or the tidal forces of the Milky Way's spiral arms could perturb the object's orbit over billions of years, bending its path and potentially redirecting it back toward the Sunday. The odds of such a return are vanishingly small, but in the vast timescales of cosmic evolution, even the improbable occasionally occurs. For now, 3IATLAS fades from view, its mysteries unresolved. Astronomers have extracted every possible piece of information from the available data, but fundamental questions remain unanswered. What drove its anomalous acceleration? Was it hydrogen, carbon monoxide, or something else entirely? What is its true composition, and where did it form? These questions will linger, unanswered, until perhaps another interstellar object arrives with similar properties, offering a second chance to test the hypotheses developed for 3IATLAS. The broader context of galactic dynamics. The passage of 3IATLAS through our solar system is not an isolated event, but part of a much larger, ongoing process that shapes the structure and evolution of the galaxy itself. Interstellar objects like 3IATLAS are the debris of planetary formation, ejected from their birth systems and scattered throughout the Milky Way. Understanding their abundance, distribution, and properties sheds light on how planetary systems form, evolve, and interact over cosmic timescales. Planetary formation is an inherently chaotic process. When a protoplanetary disk surrounds a young star, material gradually coalesces into larger and larger bodies through collisions and gravitational attraction. Small dust grains stick together to form pebbles. Pebbles accumulate into planetesimals, and planetesimals grow into planets. But not everything ends up on a planet. Much of the material is ejected, flung out of the system by gravitational interactions with the growing planets. The ejection process is most efficient when massive planets form early. Jupiter-sized worlds exert powerful gravitational forces on nearby objects, accelerating them to high velocities. If an object gains enough speed during a close encounter, it can escape the star's gravity entirely, becoming unbound and drifting into interstellar space. Simulations of planetary system evolution show that for every gas giant that forms, hundreds or thousands of smaller bodies are ejected. Over the lifetime of a star, billions of years, the cumulative number of ejected objects can reach into the trillions. This process isn't unique to our solar system. Every star with planets likely ejects material, contributing to a vast population of interstellar wanderers. The Milky Way contains roughly 200 billion stars, many of which have planetary systems. If each system ejects even a modest number of objects over its history, the galaxy should be teeming with interstellar bodies, comets, asteroids, and planetesimals drifting between the stars. The spatial distribution of these objects depends on the dynamics of the galaxy itself. Stars orbit the galactic center in roughly circular paths, but their velocities vary depending on their distance from the center. Stars in the inner galaxy orbit faster, while those in the outer regions move more slowly. This differential rotation means that interstellar objects, once ejected from their parent systems, don't move in straight lines, but follow complex, curved paths through the galaxy. The velocity dispersion, the spread in velocities among stars and interstellar objects, also plays a role. Stars in the solar neighborhood have velocities relative to the Sun ranging from a few kilometers per second to tens of kilometers per second. Interstellar objects inherit the velocity of their parent stars, plus whatever additional velocity they gained during ejection. This results in a population of objects with a wide range of speeds and directions, creating a kind of random background traffic as they crisscross the galaxy. The encounter rate between interstellar objects and planetary systems can be estimated using galactic dynamics. Given the density of stars, the typical velocity of interstellar objects, and the size of planetary systems, astronomers calculate that the solar system intercepts roughly one interstellar object larger than 100 meters every year. Smaller objects would be more numerous, but most pass through undetected due to their faintness. These encounters are brief. An object moving at 40 kilometers per second crosses the inner solar system from the orbit of Jupiter to the Sun and back out again in about a year. During that time, it spends only a few weeks within the range where it's bright enough for ground-based telescopes to detect and track. This fleeting visibility explains why interstellar object discoveries remained so rare until recent years, when automated sky surveys dramatically increased sky coverage. The discovery rate is now accelerating. ATLAS, Pan-STARRS, and soon the Vera Rubin Observatory are scanning larger areas of sky more frequently, catching interstellar objects that would have gone unnoticed just a decade ago. As the sample size grows, astronomers will be able to measure the true abundance and velocity distribution of interstellar objects, testing models of planetary system evolution and constraining the efficiency of ejection processes. But the implications extend beyond planetary science. Interstellar objects also serve as tracers of galactic chemical evolution. Each object carries a chemical fingerprint from its birth system isotopic ratios, elemental abundances, and molecular compositions that reflect the environment in which it formed. By studying these fingerprints, astronomers can learn about conditions in protoplanetary disks around different types of stars, in different regions of the galaxy, and at different epochs in cosmic history. For example, stars in the inner galaxy tend to have higher metallicities, more heavy elements than stars in the outer regions, because the inner galaxy has experienced more generations of star formation and supernova enrichment. Interstellar objects originating from the inner galaxy might therefore have different compositions than those from the outskirts. Detecting such differences would require detailed spectroscopic analysis, but even crude measurements of color and reflectivity can provide clues. There's also the question of how interstellar objects affect the systems they visit. Most pass through harmlessly, their gravitational influence too weak to perturb planetary orbits significantly. But occasionally, An interstellar object might collide with a planet or moon, delivering water, organic molecules, or even speculatively microbial life. Such impacts could, in principle, seed planetary systems with the building blocks of life, a process called panspermia. The probability of such impacts is low but not negligible. Over billions of years, a planetary system will encounter millions of interstellar objects, and a small fraction will collide with planets. Earth itself may have been struck by interstellar impactors in its distant past, though identifying such events in the geological record is nearly impossible without clear isotopic anomalies or other markers. Interstellar objects also influence the structure of the Oort cloud, the vast spherical shell of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units. When an interstellar object passes through the Oort cloud, its gravity can perturb the orbits of Oort cloud comets, occasionally sending one into the inner solar system. This mechanism may be responsible for some of the long-period comets observed from Earth, comets that appear once and then vanish, never to return. In a broader sense, interstellar objects are the connective tissue of the galaxy, linking star systems in a slow, inefficient exchange of material. Over the galaxy's 3 billion year history, countless trillions of objects have been ejected, wandered, and occasionally been captured. This ongoing process redistributes matter across the galaxy, mixing the products of stellar nucleosynthesis and spreading the chemical elements forged in supernovae to distant regions. In this way, interstellar objects are not just debris, they're participants in the galaxy's long-term evolution.